Hi, so we're just about to start. Just give me a second to set things up. Yeah. Okay, so let me start with pulling out the whiteboard. Um, Whiteboard, yeah. Okay. So we'll be discussing geometry today. Can everyone see the whiteboard? So we'll be doing the geometry problem set today. Let's see in chat. So can everyone see the whiteboard? Please don't type on the whiteboard. Yeah. Uh, yeah, just let me know if everyone can see it. Yeah. So let me know in chat if everyone can see the whiteboard. Yes or no in chat, please. Great. So people can see the whiteboard. That's great. Yeah. Also, while we still have access on, please don't please don't type anything on the whiteboard. If you have any questions, you can type in chat or ask me directly. Yeah, sounds good. So we're going to do our geometry problem set. So let's start with the very first problem. So we have these three concentric circles. These three circles. And we have this angle coming out over here. So now if you look at this shaded area, so the radii of the circles are 1, 2, and 3. This shaded area. And what was the remaining portion? Was the remaining portion? Yeah. And the entirety of the second annulus. Yeah. So this sort of shaded area here, which is the entire second annulus and sector part of this thing, of the third annulus, third ring. If this is equal to the unshaded area, okay, this is equal to the unshaded area, then we have to find what this angle over here is. Let's say this angle is X degrees, something. So let's just try to find out what's going on. So if you look at the total area for this whole circle, then the biggest radius is 3, right? From O to B, radius is 3. So the area is pi r squared, which is the area of the circle. So area of big circle, right? Can everyone see my cursor? Yes, no in chat, please. If you can't see my circle, if you can't see my cursor, let me know. So this is the area of the big circle. Yeah. And so the shaded area is half of this area, right? Because we are covering the shaded part and the unshaded part together, and the shaded and unshaded part have equal area. So shaded area is half of this thing, is half of pi r squared, which is half of pi times 9. So it's 9 pi over 2. That is the total shaded area, right? Yeah. Okay, we have this. And let's see what else we have. Now let's actually try to compute based on this angle X, what the area for these objects is. So one thing is that we are saying that we have this entire second annulus. So second annulus is simply, let's call this x over here, y over here. It's simply the donut shape between the OX circle and the OY circle. It's the donut shape. And we have this entire area as part of a shaded area. And then on top of it, we have this other sector type of area over here, right? This BOC sector, where you just have the third annulus. So second annulus area, we can also calculate. So the second annulus area is simply area of the entire second circle, just pi r square, pi 2 squared, minus area of the inner thing, minus area of the inner circle. It's pi 1 squared. And so this is 3 pi, right? So you have 3 pi is this area over here. And now you want to just find this area, this specific, the dark shaded area, which I'm shading right now. You want to find this thing, right? So that would be equivalent to finding the area for the sector BOC and subtracting the area from the sector in the same angle, but on the second annulus. Like you compute this entire big pizza slice, and then you subtract off the smaller pizza slice over here, right? So the area, so if the angle is x, then let's say the total angle is 360 degrees, or total angle is 2 pi radians or something. So yeah. Or I'll actually just do it in terms of 360 degrees because people are more comfortable with degrees. So x over 360 degrees is the portion we have right now, right? So x over 360 degrees is the portion we have right now, times the area of the third sector, which is pi times, so this times the area for the whole big circle, which is pi times 3 squared, will give you the area of the big sector from OB and OC, right? And then you subtract off the same part, which is this times pi times 2 squared, right? So you subtract this part off. Also, just give me a second. Just give me a second. I'll be back. Yeah, sorry, I'm back. There's some background noise. Yeah, so we have this, and this is equal to x over 360 times pi times 9 minus 4 is 5, right? So it's this thing. So it's x over 72 times pi, right? Yeah. So now when we do the calculation, we'll get 9 pi over 2, which is the total shaded area, by just taking half of the total area, is equal to 3 pi, which is the area from the second annulus, plus for the second annulus, and then we are looking at just this sector, this outer sector, right? So the outer sector should be like, should be this x over 72 times pi, plus x over 72 times pi. Okay, so we cancel out the pi from all of these, and we get 9 by 2 minus 3, which is 1.5 times 72 is this angle x, which is equal to, I think 108, yeah, 108 degrees. So this is equal to 108 degrees. But the actual number, maybe even if you do some calculations wrong, the actual number is less important than the geometry. The idea of the geometry here is that you want to think of this shaded area in pieces which are easy to calculate. So you can think of it as the second annulus, and you can think of it as the remaining sector over here. Does it make sense? Is everybody on board? Is everybody comfortable with this? Let me know if everybody's comfortable. Then we can move on. Yeah. Yeah, just let me know, guys. Let me know if everybody's on board. Yeah. Okay, so if no questions, we can move on to the next question. So which question do you guys wanna try next? Any suggestions in chat? Easy? Yeah. Yes, this one was not too difficult. It's just like once you have the correct idea that you want to think of the shaded area as splitting it into two pieces which are easy to calculate, and then you just calculate out using standard formulas. It's nothing very surprising. Yeah. All right. Let's move on to the second one then. So second question says we have a paper triangle ABC with angle C is 90 degrees. Okay. And so we have paper triangle this, which is right angled. And you have, let's say, A over here, B over here. And this is like a 3, 4, 5 triangle, I think. So this would be something like adjusting my screen size. Yeah. So this would be 90 degrees. And BC is 3. Okay, so this is 3. CA is 4. This is 5. Okay. And now you fold this triangle so that A goes to B. Like you fold this triangle. And so it's made out of paper. You're folding it so that A goes to B, right? And you'll make a crease inevitably. When you make a fold, you'll have a crease, right? You'll have a crease somewhere. So you have to find the length of that crease, right? So the idea is that when you fold it, A should go to B. Now let's think about it generally outside this triangle picture. Let's say you have a piece of paper and you're trying to fold something and you want A to go to B. Where would you want the crease to be? Like how would you fold the paper so that A reflects onto B? So crease will be some line and the reflection of A in that line will be B, right? Crease will be some line. Let them intersect at M. Then the reflection of A in this line L, which is the crease, will be B. So A comma B, reflection is in crease. So there are reflections in the crease, which means the crease has to be the line such that it passes through their midpoint and is perpendicular. So it should be the perpendicular bisector of AB. So crease must be perpendicular bisector of AB. Is everybody okay with this so far? Everybody comfortable? And if you want to see it in detail, you can see it this way. You can say, let me pick a point P on the crease L. Then PA must be equal to PB by the reflection property. PM is common. And the angles over here are the same as 90 degrees. So these are congruent triangles. And so when they're congruent triangles, you also get AM equals MB. You get this. Yeah, so there's many ways of seeing it. But the idea is that it'll be the perpendicular bisector. So you draw a perpendicular bisector over here. Let's say this is M. This is N. And you draw this nickel bisector over here. Yeah. Well, now you can do something interesting where you can observe. If you want, you can do it by Pythagoras theorem and just calculate out a bunch of stuff, but you can just observe something interesting, which is, so I'll show both approaches, maybe that'll be useful. So one thing you can observe is the triangle AMN. So if you've seen similar triangles, you can observe this. It's similar to triangle ACB. You can observe this. And now MN ratio AM, so MN divided by AM, is equal to CB ratio AC, equal to CB ratio AC, which is 3/4. And AM is simply half of AB, which is 5/2. So this is 5/2. So from this similar triangle pairing alone, you get MN equals 3/4 multiplied by 5/2. It's equal to 15/8 or something. Something like 15/8, I think. So that's one way of doing it. Another way of doing it is using some kind of Pythagoras theorem type of idea. So let's say Mn is equal to X, and you don't want to do this similar triangle, but you still have this as 5/2 over here, which is AM. So you can compute the length AN. So you can compute AN as AN square is given by 5/2 square minus X square. So it's 5 square by 4, or 25 by 4. I'll not even say 5 square. 25 by 4 minus X square, right? And AN square is equal to BN square, because AN and BN are equal. So this is equal to BN square. And BN square is equal to 3 square plus CN square. So this is 9. And what is CN now? So let's actually compute what CN is. Maybe the picture itself is incorrect. Let's see. Maybe the picture is incorrect. M is 15/8, and this is 5/2. And picture looks fine. Picture should be fine. So CN is 4 minus AN whole square. Okay, maybe I should choose a different variable than this being X. Also, this is plus. Sorry, this is plus. Actually, that makes a lot more sense. Yeah, X squared plus 5/2 square is AN square. Okay, and this thing is equal to 4 minus AN whole square, right? That is CN. So it's 4 minus AN whole square. So when you simplify it, AN square is equal to, so let's AN equals Y, just to make the notation easier to write out. Then you have Y square is equal to 9 plus 4 minus Y square. And so I'll just expand the 4 minus 1. Y square is 16 minus 8Y plus Y square. Yeah. And so you cancel off the Y squares, and you get Y is equal to 25/8. So you get Y is 25/8. And so you have Y square over here now, which is 25/8 whole square. That'll be like 625 by 64. This is going a bit out of hand. Okay, maybe not so bad. Maybe not so bad. Let's actually just try. If there's a calculation mistake, we'll see it immediately. Or we should rather. So you subtract from 625/64, you subtract 25/4, you get like 16 times 25 is what? 400. So you get 225 by 64. Yeah, okay, that makes a lot of sense. So you get 225 over 64 is equal to x squared. And then when you take the square root, you get x is precisely 15 over 8. So 15 over 8 is equal to x. Because x is positive, you don't care about the negative roots. Yeah, so there's two ways of doing it. Either you can do it using similar triangles, and then you can get this, which is quite direct, or you can use Pythagoras theorem and just compute all the lengths, and then just try to use all possible conditions available to you. Like exhaust all these conditions, and then you'll end up solving for x. So both approaches work, and both approaches will give you the same answer, as they should. So, yeah, okay. Any questions about this one? Is everybody comfortable with this one? Just let me know in chat, yes or no. Yeah, waiting for responses in chat. No question, both methods are clear. Okay, that's good, that's good. Yeah, I just want to make sure, because we shouldn't be rushing past. These two questions were sort of more similar to what you might see in school and using like similar techniques. And I think other questions will be mostly the same, but as we go through the examples, they'll start using some more technology. Not much, but maybe something like PowerPoint, which I'm not sure if it's always there in school. Yeah. So let's try doing, I'll wait for a couple more responses and then let's just try doing the next problem. Yeah. Okay. I'll just wait one more minute. Let me know if any questions about the first two problems so far. Otherwise, we can move on. All right, let's just do example 3 then. I think everyone seems okay with it. So yeah, let's just do example 3. And this one's a bit more tricky. So there's some more work to be done, which I think is good if you want to do geometry later on as well. So you have these two rectangles, A, B, C, D, and this other big one. So you have these two rectangles. Let me correctly label them. A, B, C, D. What else was that? E, F, G, H. Okay. E, G, H. You have these rectangles and you have the following side lengths. So you're given some lengths of sides as well. BC equals 16. Maybe I should draw these differently or write these elsewhere. I'll maybe just write them in the picture itself. So BC is 16. What else is given to us? AB equals 107. So AB is quite long. We just don't have it in the picture. So AB is quite long. FG is 17. So this is also not very long. This is comparable to BC. And then EF is 184. So instead of EF, because it's kind of oblique, I'll just write HG because it's equal to EF, and this is 184. So EF equals HG is what we're using here. And now you have to find the length of CE, given the following condition. You're given that there exists a circle. So you're given that there exists a circle which passes through these 4 points. Not terrible for a hand-drawn circle. Not the worst, right? Yeah, this is not bad for a hand-drawn circle with a trackpad and all this. Yeah, so given ADHD cyclic, find the length of CE. So we have to find this length x equals CE over here. Given ADHD cyclic. First, I'm curious, like, what are some ideas in chat? Because this is a, I think, relatively new type of idea. Maybe students who are younger who have not seen enough geometry would not know the idea, but at least what are things you would want to try given the cyclic condition? Because this could also be an interesting discussion on its own. So maybe throw out some ideas in chat, guys. Like maybe let's have some ideas in chat before we proceed to do some calculation, do some maths. Like, how would you want to attack this cyclic condition? Mhm. I mean, I'll show you both approaches. I'll show you two approaches to this, I think, because I see another approach which I did not see before. So we can try both. But yeah, I think this is going to be instructive. So I'm curious how people want to tackle the cyclic condition. There's one approach which is more natural, which I think you guys will see more readily. One approach which may require some extra theory. So just curious, what people want to try. Ptolemy. I mean, not impossible actually. Let's see. I mean, you can compute the diagonals, I suppose. And okay, one of the diagonals will be in terms of this, but x, but that's okay. And then what else? I mean, both the diagonals actually will be in terms of x, so that is possible. dh. Okay, so that is fine. Okay, so if you want to compute using Ptolemy, you can. That is definitely possible. Let me quickly mention. I think your idea is something like ah times dg. So this is possible. I'm not saying it's ideal, but I think it's possible. Is AD times HG plus AH times GD. So what one can do is compute each of these lengths using this variable x. GA, sorry. Oh, sorry. DH times GA. So this would be like Ptolemy's theorem. And one can just like compute each of these lengths and then just multiply all of them, get a huge bunch of square roots involving x squared, and then expand everything, solve for x. So this is possible if you know Ptolemy's theorem, and if you're very courageous with calculation, because I will not want to write this with a trackpad. It's certainly possible by hand, but with trackpad, this will be quite bad, I think. DH and GAT are similar. Okay, so you want to construct a similar triangle. QB and G. What is QB? Oh, you mean CB? No. QB and CB. Someone messaged a good idea, but I'm not sure what. Oh, sorry. AB. I see. I see. AB and GF. Okay. 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 Uh, they're similar and. Hmm. And this is a promising idea. Like, I don't know what the full continuation is, but this looks like a very good idea, to be honest. So you're constructing this new point and then trying to use similar triangles. I think this should work out. Like, almost every idea which addresses the cyclic thing should work out. It's just like how quick and efficient the calculation will be. But the similar triangles idea is very good in chat. So yeah, great idea there. Yeah, what I'll suggest is, okay, so I'll suggest something which is a fancy approach, and then maybe we can try a lukewarm approach. So one idea is that you, let's say, extend this whole thing through E and let it meet at T. So this is one approach. And then you have these two are parallel, right? So these two are parallel, which means that you have this as an isosceles trapezium. So TADH is an isosceles trapezium. An isosceles trapezium. Yeah. So in particular, if this thing is 107 minus x, 107 minus x, and this thing is what? 184. Yeah, this whole thing is. And also, let's say you extend it over here on this side as well. And let's say here you get S. Okay. And so this, you get this as S. Then you can use something called power of point at E. So what I mean by that is triangle EDH. So this may be similar to your similar triangles idea. I think this is actually pretty much the same idea. Yeah, no, you're right. So your similar triangles idea works perfectly. Yeah, it's the same proof. EDH is similar to triangle ETS. Why? Because this angle over here, I'll just draw a dotted line. Yeah, is equal to this angle over here, and this 90-degree angle is common, so the third angle is also equal. So they're similar, which implies when they're similar, you get ED times ES. You get this thing, ED times ES is equal to EH times ET. Yeah. And these are all depending on X. So we can now actually compute it in X, and there's no square roots either. So it's a bit easier. So this is 107 minus X, which is ED, multiplied by, what is it? What is it over here? It's X plus, okay, so it's 184 plus 107 minus X. Okay, that's a horrible number. It's like 291 minus X or something, like not great. Oh yeah, I think the meeting is being recorded, so don't worry about it. Don't worry about it, guys. So you get this thing. I'm not sure. Okay, there's a very high chance I'll do something wrong with the calculation, so you guys should make sure the calculations are correct. Yeah. EH. And now EH is just 17. Okay, so that's just 17. Okay. Multiplied by ET. And ET now is this 16 plus this length over here. And let's call this K. So KT is same as EH because of the isosceles trapezium. So it's 16 plus this, which is 17, because EH is 17. So this was 17, this was 17, and so KT will also be 17. So it's like 17, and this is EK is 16. So adding them is 33. So this is 17 times 33. Yeah, so this is what you get over here. Maybe I'll make y equals 107 minus x just so that this variable is a bit easier. It's not that bad. Sure. I think you're right. I think you're precisely right. Indeed. Yeah, constructing this I is also perfectly great. So yeah, this also works. So great solution in chat. I think it's actually a faster way of getting it if you don't know power of point. So this particular relation is called power of point, which is for any point P, E inside the circle. If you draw two lines, you get ED times ES on the same line, the same as EH times ET on the other line. So I just want to introduce this idea, but if you just notice that you can introduce a missing corner in EDH, then that also works. That also solves the problem. Or even in FCB, that also solves the problem. So great solutions in chat. I'm happy to see chat already has like good ideas which are faster than this. And I just want to show the power of point idea. Okay, so it's y times y plus 184 is equal to 17 times 33. So I can make it like 3 into 11 into 17. So even without solving the quadratic equation, you can kind of guess what's happening here. Because 11 times 17 is 187. So you can use the quadratic formula, or you can sneak your way out of it by just noticing y equals 3 works, which implies x equals 104. X equals 104. So this is the final solution over here. All right, so this is one way of doing it. There's other ways in chat. I'll just highlight them. One idea is that you extend these two over here to get this point I. And then you notice a bunch of similar triangles. You notice that IDH is similar to IGA, which is also the power of point. It's kind of the same idea with E, but with the point E outside. So you're using the point I instead, and you have two lines through I. So IDH is similar to IGA. And using that, you can compute what these lengths are. So you can find out what's going on there. Yeah, because IG over I, yeah, you can just compute this. So I won't bother making too much of a fuss about it, but you can just compute directly using this. And you'll get something similar. I think you'll get something similar to what we had. But yeah, you'll get something like 107 minus x divided by 17 is equal to this IG divided by IA, which you can find what these lengths are. And then you'll just get a single variable equation, quadratic equation in x. Similarly, one approach in chat was to extend this side and use this corner over here. So you can use either corner. I think both are fine. The other approach I wanted to mention, because it might be just like a more rudimentary approach than this kind of tricky similar triangle stuff, is just actually look at the center. So let's say O is the center, and then see where O is coming from. O is coming from these perpendicular bisectors, right? So O is coming like this. And so this particular portion, let's call this HM, and yeah, this DN over here. So we have stuff like this over here, right? So with these two perpendicular bisectors, we already know OA is equal to OD. And we also know OH is equal to OG, right? So the only thing that we need to check as a condition for this to be the center is OD equals OH. So we just need to check OD is equal to OH, and that will tell us what the actual equation for O should be. What should O satisfy for this to be the actual center? So we want OD equals OH, and we can compute that, right? We can compute what OD is. So you have 107 minus x plus half of this 184, which is 92. I think this is 92. So you have this plus half of AD, and AD was what? AD was 16, so this would be 8. So you have like OD square is equal to 8 square plus 199 minus x squared. So you can get this. And we can also just check that we are not doing anything insane, because this is like 95. X is 3, so this is like, oh, sorry, x is 104, so this is like 95 over here. So you're doing 8 squared plus 95 square over here, and then OH square, we can similarly compute. OH square, this should be, again, so this is 92 again, and this one is, so it's all of this length, which is 17, plus half of this length, which is 8. So this is 25. So this is 25 square plus 92 square. Okay, and then we are subtracting 95, 8 square from all of this. So maybe if you just show quickly by back of the envelope calculation that this thing over here, that's 92 square, is equal to 25 square minus 8 square. Then we're like good to go. And so it's like 624 minus 64. That's what? You subtract 24 and then you have like subtract 39. So it's like 561, I want to say, which if you just divide out by 3, you get 3 times 197. Yeah, so 3 times 197, which is precisely 95 square minus 92 square, because you have difference of squares is 3, some of them is 197. So yeah, so this will automatically tell you x is 104 as well. I'm just checking that this is not an incorrect equation. Yeah, and then you can just check, you get the same answer. How many questions are due until now? So this is just the third question, right? So we still have many more to go. Unlikely we'll be able to solve all of them in the meeting, but let's just look at ones which I think are more adjacent to SLMC. Then the later ones like 7, 8, 9 are probably a bit out there. Yeah. Like the later ones are not directly relevant. They're more like, I think later on when you prepare for the Olympiad, but these are more computational. All right, so is everybody okay with this? So both of these approaches will give you what you want, and all three of these approaches actually. So you can introduce the corners and then do power of point or similar triangles. Just do power of point at E, or you can work with the center and then do it directly. Just directly calculate everything. And that's kind of the general motif for all geometry problems, is that you try to want to have all the conditions in front of you, and then if you just start writing out algebraic equations using those conditions, there's no way you can't solve it in some sense. So you should be able to solve it, and yeah, you should be able to do it. The only question is, how do you do it efficiently? How do you do it in a way which is clean, which is easier to come up with? And that's probably the main aspect for all computational problems. Later on, when you're trying to prove stuff, that's a bit of a different story. But for this type of computation, it's just like try to write out all possible conditions that need to happen for the problem to be true, and compute each of those conditions. So that's what the philosophy is so far. Okay, so now we can move on to maybe question number 4, if people are okay with question number 3. So I'll just wait in chat if everybody's comfortable with question number 3. Yeah. It'll be the PDF. Let's see. Let me see if I can resend the PDF. Okay. These should be in the. Just check if this is okay. Yeah. Okay, I'll just wait out for any questions about question number 3. Wait 1 more minute, and then we can move on to question number 4. Let's wait a couple more minutes because I want to make sure everybody's okay. Unless you just let me know in chat by yes or no that everybody's okay, and then we can move on. So let me know. Yeah, let me know, guys, if everybody's okay, and then we can move on. Ooh. Yeah. Okay. Okay. So there's a couple of okays and DMs. It's good. It's good. Yeah, a lot of these questions are from the AMCs and the AIMEs, the American Math Competitions. So that's actually a pretty good source of practicing computational geometry. Like I didn't mention the source in the handouts because then having a source is not the best. But yeah, I think that's worth knowing is that that's a great source of doing these computational geometry problems. Yeah. Okay, let's move on to question number 4 then. So we have to find the angles of this triangle ABC, where we are just given a diagram with a bunch of equal segments. So see, we draw this parallelogram. Okay, and then so and these two are equal. And let's see. It's a bit of a puzzle here, just having all these equal things. This, then you have this, and yeah, this is equal. So all these are equal, and that's given to you. And you have to find the angles of triangle ABC. Okay. So how do you want to do it? How do you want to start? So one strategy for these type of angle problems is you just start anywhere and then try to sort of DFS your way into it, like try to, or even more like BFS your way into it, try to get all possible angles you can from this source, and then just try to compute the same thing in a different way. And that should usually just tell you what all the angles are. So let's say this is angle X. Because these are equal, because at this vertex you have an isosceles triangle, this angle will also be equal to X, right? And it's not implicitly mentioned, but maybe we can even just show it's a, yeah, both pairs of opposite sides are equal. So this is a parallelogram in any case. Yeah. Yeah. So this thing, yeah, so this will just carry over to here. We'll have this is equal to X. And we'll have now by isosceles triangle, this is also equal to X, which means this is equal to X. Yeah, let's see. And then finally, this thing will be equal to, let's say this is equal to Y, then this is also equal to Y, and their sum is X. So X equals 2Y. So we get X equals 2Y immediately. We also get X plus Y equals 180. And so now you can just compute everything. Now you have 2X plus Y, which is 5Y, and it's equal to 180. So this implies Y equals 36. So it's a bit of an easier problem. Perhaps I should have placed this earlier compared to the other one. But it's an easy calculation, but just like you have to notice that this is a parallelogram, or this is parallel, and then you have to notice all the isosceles triangles here. So for example, this is 180 minus 2Y. Oh no, sorry, this is just Y. Yeah, minus 180 minus 2x. Sorry, yeah. And minus 2x. And so you get 35 degrees is y, and then x is 72 degrees. So A is 72, B is 72, and C is 36. Yeah. Yeah. Ideally, okay, if this was a proof type of thing, you should probably also check that for given such a triangle which is 72, 72, 36, there exists such a quadrilateral inside. So in that scenario, you should ideally check this as well. But if you're just given to compute the angles, if this is true, then this is completely correct. So yeah. Yeah, so it's a bit of a quick problem, not much calculation here, just noticing these angles. Is everybody clear with this? Everybody okay with this? So yes or no in chat, please. Okay, if everybody's okay with it, we can move on to the next one. Move on to problem number 5. So for problem number 5, we have a similar type of problem, but many more angles and many more equal things. So not the easiest to draw by a trackpad, but let's see. So you have this equilateral XYZ in the middle, or rather it's like XCY or something. I don't know. Okay, I'll erase these and draw them again. It's like XCY. That notation is important, but still, let's just stick to the notation. Now you draw a bunch of other stuff. You draw a C over here. You draw an A over here. And you draw a B over here. Okay, so you draw these. Oh, they're not called ACB either. Okay, the notation in this problem is not that great. ACE for some reason. Okay, and then you join A and E, but then you have a B and D somewhere. Yeah, you have this thing over here. So this is B, this thing over here, which is D. So we have all of this. Now we are to write a bunch of equal lines here. So this is also equal with the dash. This is also equal with the dash. These are equal with double dashes. So they're not equal to the previous lengths, but they're equal among themselves. Okay. And then these are also the same double dashes. They're also equal with all the dashes are equal to each other. All the double dashes are equal to each other. This, this, and then these two. Oh, wait, what happened? Okay, no, it's fine. It's fine. Yeah, so we have all of this. And now you have to, yeah, now what do we have to do? Find the angles of the pentagon. So you have to find all angles of the pentagon A, B, C, D, E. So it's a much worse, much worse angle chase. Find all angles of the pentagon A, B, C, D, E. Basically find every angle in this picture that you can think of. So firstly, let's start with this being 60. So this is 60. And we have a very common archetype of a triangle. So we have a triangle like this where two sides are double dashes and one side is a single dash. And all such triangles are congruent. So we just need to have like a common notation for all of them. So that if I call this 2x, this is 90 minus x. And the other one is also 90 minus x, right? For now, I'll just say 90 minus x equals y, just so I don't have to write 90 everywhere. Equals y. And now we are ready to angle chase. So now we can angle chase a bunch. So this will be y, y, yeah. And then AZE is something we can calculate, but we are kind of at a dead end the moment we do that. So, okay, that's one way of doing it. And you have a y over here. You have a y coming from here. You have a y over here. And then you have a y over here. So you have 4 y's around this point x. And then you have a 60 degrees inside. So 4y plus 60 is the angle around x. Is equal to 360 degrees, which is the angle around x. So this implies y is 300 by 4, which implies y is 75 degrees. And this implies x is 35, okay? Sorry, not 35, x is 30. What am I saying? Yeah, x is 30. So we have x and y, and now we just need to calculate everything which exists in the picture. So each of these is x. So when you combine all of them, all 3 of them are x, you get 3 times x, which is 90 degrees. So angle C equals 90, which does not look like it, but it is 90. So what can we do? Now let's compute angle B. So this is 2y. 2y, and similarly angle D is also 2y. Both of these are 2y. Okay. So angle B equals angle D equals 2y equals 150. This is 150 degrees. Now let's compute angle A and angle E. So angle A right now is like 2x plus something. 2x plus, I will say z, which is the angle downstairs. So I'll call this angle ZAE to be z, which is equal to ZEA. This is also z. And E also has 2x. Yeah. So what we have is angle A equals angle E is equal to 2x plus z. And we can just calculate. So we can calculate this little z in 2 different ways. So AZE is isosceles, which implies angle AZE equals 180 minus 2z. Which implies the 360 minus angle AZE is, so 2y plus 60 is 360 minus AZE. So we can do it this way. And we'll get 180 plus 2z. And now we know what 2y was. So y was 75, so 2y is 150. 150 plus 60 is 210. 210 minus 180 is 30. So z is 15 degrees. Z is 15 degrees. And now you have 2x plus z. So x was 30 degrees. 2x is 60 plus 15, so 75. So each of these are 75 degrees. A and E are 75 degrees. Yeah. So that's one way of getting A and E. So you have 75, 150, 90, 150, 75. These are all of the 5 angles. Let's just quickly make a sanity check that these are correct. So if I add all of these angles, if I add all of them, 75 plus 150 plus 90, these are the 5 angles. 150 plus 75. So 75 and 75 will make a 150, and you have 3 copies of 150. So it's 3 times 150 plus 90. And this all together combines to 540, which is what you expect. So for a pentagon, the sum of all angles should, for convex pentagon, sum of all angles should be 540 degrees. In general, if you have an n-gon, you can fix a vertex, draw all triangles to get a triangulation, and each of the triangles has some 180 degrees for angles. So total sum of angles for the pentagon is n minus 2, because there's n minus 2 triangles, times 180 degrees. And so here it's 5 minus 2, which is 3, times 180, which is 540. So everything's correct. We didn't make a calculation error either. This was a good sanity check. And then we have all this happens. Now, of course, if this was like if this was a proof-based competition, you might even be required to prove that such an XYZ exists inside this pentagon. But yeah, here, if you just have to compute the angles, you just have to compute the angles. It's as simple as that. Yeah. Any questions about this one? Is everybody okay with this calculation, this problem? I'll wait a couple of minutes and then we can go to the next one. Someone DM'd me. So, okay, let's see. We diagonal. Oh, is this for the next problem? From P to AC and BD. Okay, sure. NOM is rectangle. Area square is this. I don't know what the answer is, but this looks correct to me. So, or at least the approach looks good. So it should be fine. I just quickly took a glance and should be fine. So yeah, let's for the next problem. Any questions about this problem, guys? Or the previous angle chasing problem, and then we can move on to the next stuff. Just yes or no in chat, please. Yes or no in chat. Yeah. Okay, if no questions, then we can move on to the next problem. Okay, so let's move on to question number 6. So this is, you have point P in the circumcircle of ABCD, which is a square. Okay, so you have ABCD. ABCD. And you have point P on the square on the circumcircle such that PA times PC is something, and then PB times PD is something. Yeah. So you have the square. Yeah, and you have all this. Okay. Mm, yeah. Mm, yeah. Okay, so you have P times PB equals this, and then something else equals. Okay. Uh, so yeah, okay. So maybe it's worth, okay, maybe it's worth mentioning a formula, which is, it's probably a bit harder problem than I anticipated, because maybe there's an easier way, but the formula I can best think of is not the simplest. So let's look at this following picture. And if you've not seen this before, that's completely fine. You can just think of this as a new formula you learn every day. Yeah, it's not necessarily amenable to easier things. So one approach could be that you can, for example, draw a perpendicular from P over here and just try to do all coordinates. So let's say this is X, and you try to compute AP using this X, you try to compute PC using this X, and so on. So you can do that type of thing. Like, that is likely fine, but we can try doing something better. Is also the case that we can try doing something better. So maybe, okay, first I'll try using this geometric idea, and then we'll see if the algebraic computation is any easier. I don't suspect it is easier, but let's see. So if I draw a diameter, PP prime is a diameter, let's say, then this is 90 degrees, and let's say this was K. So now triangle PKA over here is similar to triangle PCP prime, which implies PA times PC is equal to PK times PP prime. That's one way of thinking about it. And this is, in general, when you learn Olympiads, this is something called root BC inversion, which takes K to P prime, but we don't need to worry about it right now. Another simpler way of seeing this is as follows. If you have triangle ABC, then the area of the triangle can either be half of A times the altitude from A, or it could be half BC sine of the included angle, right? Which is also a pretty common formula, which also comes from the same thing pretty much. So you can do this and then cancel off the half. Now you can also use so this is A over sine A, HA is equal to BC. And now you can use the sine rule, which says A over sine A is 2 times the circumradius. So it's 2 times the circumradius multiplied with the altitude from A is equal to BC. So you can use trigonometry, or you can use this type of similar triangles. And either way, the idea is that you can draw this perpendicular from P to this. Let's call it M. Or maybe let's use someone else's notation. I want eminent only for midpoints. So let's say this is, let's call this X, let's call this Y. Okay. So draw perpendiculars X and Y. Okay. Then 2PO times px is given to be pa times pc, or rather we know it's equal to pa times pc, and that pa times pc is given to be equal to 56. In the problem statement, we know this is equal to 56, right? And the other thing is 2po times py is equal to pb times pd is equal to 90. Yeah. Okay. Now let's call this 2po, which is the diameter. Let's call this let's call the whole diameter to be like x or something. Then px is 56 over x. Okay, and py is equal to 90 over x. So we have both of these. Okay, we have both of this. And the area that we want for ABCD, we want the area of ABCD, right? That is 2x squared, because 4 times half of x squared. Okay, so now we have px and py, and this is also 90. This is also 90. So px over y is a rectangle. Okay, we have this. Okay. What else can we compute now? Now we can just do like a Pythagoras theorem, perhaps. So PO square is OX square plus PX square. So PO square is equal to OX square plus PX square. Okay, we have this. And OX is PY because of the rectangle over here. Because PX OY is a rectangle. PY square plus PX square. This is PO square. Okay. So now we have x over 2 whole square, which is PO square. So x over 2 whole square is equal to py square, which is 56 square by x square, plus, sorry, py square was 90. This, so, okay, I'll just rearrange the terms. 90 square by x square. Okay, we have all this, which implies, okay, now I'll just make x equals 2r because maybe that's a bit easier. X is 2r is a bit easier, and we just need to find r. So r square is equal to 28 square by r square plus 45 square by r square. Square by r square. This implies 2r square is equal to 28 square plus 45 square is like, can we compute this thing? Or 2r square, no, so 2r to the power 4 actually. Oh gosh. 45 square. Is this correct? Looks okay, but I don't know. So can someone calculate the 28 square plus 45 square? So let's see. This is 2025. And then this is like 744. What is this thing again? 28 square. 784 maybe? Yeah, 784, yeah. Not 744, 784. Okay. So you have 28 rather. When you add them, 09, 2809. That sounds like some 53 square type of thing. Yeah, this is like 53 square, I think. Right? So this is 53 square. Yeah, it is 53 square. Okay. So this thing is 53 square. Okay. Yeah. So 2r to the 4 is 50. So, okay. So now r square is equal to 1 over root 2 times 53 square. Something like this, right? Unless the 2 should just go. Oh, 2 should just go away, right? Ah, yeah, there's no 2. It's not 2r squared. It's just r squared. Ah, it's just r to the 4. Sorry. No, there's no 2. Okay, that makes a lot more sense. Yeah. I was like, where's the root 2 going? So r squared is just 53. So r squared, where r is this part of the square, like O, and then if this is r squared is equal to 53. So r into r by 2. So r squared by 2 is area of the quarter triangle. And so you multiply. So 2r squared is what we're looking for. 2r squared is the total area, which is 106, right? So 106 is the total area that you're looking for. Yeah, that solves the, yeah. Okay. Yeah, I was confused because I was getting this 53 squared, but then I was like, where's the 2 coming from? But then we also already canceled out the 2 over here when we did x equals 2r. So there was no issue there. Okay, so by just reasonable calculation, we were able to get this. Okay, any questions about this one before we move on to the next problem? Any questions in chat, guys? Before we move on to question number 7. Wait a minute. I'll just wait a minute. Are there any questions? And then we can move on to question number 7. What's the name of trigonometric theorem did you use? So I just, that's actually a good point. Yeah, I should mention it. So in any triangle ABC, if you have this angle is A and the corresponding side is A, and let's say the triangle lies inside a circle. So this is a circle which passes through 3 vertices called the circumcircle, and this circle has a radius r, right? Then you have a trigonometric relationship, which is that length of the side BC divided by sine of the angle opposite to it, sine of A, is equal to 2 times the circumradius. It's 2 times r. In fact, this is equal to B over sine of B. It's also equal to C over sine of C. So this is called the sine rule, or law of sines or something. I don't know. Sine rule is what I used to call it. So this is sine rule in a triangle. So this is the trigonometric rule we use, and it may be not very common in like before calculus classes, or maybe not in like school before calculus, but I think it's worth knowing for all kinds of Olympiad. Like if you know this rule and if you know the cosine rule, you're pretty much good to go for every trigonometry calculation in these kind of competitions. So, but this is quite crucial. I think this is worth knowing. So you should, yeah, maybe do some practice afterwards using this idea. Yeah, and then we use the fact that the area of the triangle can be written in 2 ways, like this. Both of them come from the same setup, so it's not too new. But yeah, half of A times the altitude and half of BC times the sine of the included angle. And then we just do this calculation, where A over sine A becomes 2r, and then this becomes h. So that's a good question. That's a very good question, because I think everybody, either you've seen it before or you can learn it now, but sine rule is quite crucial. I'll recommend everyone to have some idea about this. Unless you're like very young, unless you're maybe like 6th, 7th grade, in which case you can probably wait out a couple of years as well. But it's just not too hard. Like this is pretty reasonable. It's not too difficult, but it's very, very useful. Like if you're doing any kind of calculation, using circumradii, using the angles of a triangle, sine rule is quite handy. It's quite useful. Yeah, any other questions? Yeah. All right. If no other questions, we can move on to the next one. We can move on to question number 7. And okay, the diagram is too hard for this to draw, so hopefully I can screenshot this diagram. It is too hard to draw this diagram. There's 7 circles on top, and there's like 6 in the middle, and that is crazy. Okay, I don't think I can draw it by hand. Tangent to one another and to the sides of the. Okay, this is just kind of terrible, to be honest. No, I mean, what even is this, dude? Okay, it's easier to solve the question than to draw the diagram by hand because there's too many circles. But I'll just tell you what it roughly looks like. Like roughly you have this configuration. Are they touching as well? Yeah, they're also touching over here. So you have these circles which are all touching each other. And you have this whole rectangle. And all these circles are congruent. In the top row, you have 7 circles. In the middle row, you have 6. In the bottom row, you have 7 again. And all of them are congruent to each other. So you have to find the ratio of the length and breadth of the rectangle. Like if this is L, this is B, you have to find L over B. Like express it as like some half of root P minus Q, whatever. But this is what you have to find as a ratio. All these circles have equal radius. Maybe we can even assume they're like radii 1. Yeah, I think we can. No specific thing about the radius is mentioned, so we can assume pretty much anything. We'll just take arbitrary general radius. Okay, so if you squint at the diagram a little bit, you'll see that these centers have to be collinear because of tangency and because of a bit of symmetry. So we have a bunch of tangency and symmetry. Now each circle on the top row has like 2r as its total width span, and there are 7 of them. So L is just 7 times 2r. That is 7 times 2r, which is 14r. The more tricky thing to compute perhaps is B, because B is not very obvious now. So B, okay, we can remove away 2 of these things. So B is, this is R, this is R. So we already have a 2R component inside B, and we need to find this tangent length over here, which is same as this join over here. So we need to find this X over here, right? Yeah. Okay. And now look at this triangle over here, which I just drawn. All of these lines joining these centers have length 2r because the circles are tangent. So we have these triangles which have 2r, 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 which means that they're equilateral triangles, right? So this means that the internal angles must be 60 degrees. So this angle is 60 degrees. And so this angle is 120 degrees. So this angle over here is 120 degrees. And these smaller angles are now like 30 degrees. 30 degrees. So you now have a triangle which is something like this. So isosceles, and the isosceles because of symmetry. This is 120. This is 2r. This is 30. and this is some x that we are trying to find. So what you can do is, again, use the law of sines or use the sine rules. This divided by sine of 120 is equal to 2r divided by sine of 30. And if I'm not mistaken, this is same. Okay, this is sine of 60 because 180 minus theta, sine 60, which is √3/2 in the denominator, and this is half in the denominator. So what you get is something like x over √3/2, so which is like 2x over √3 is equal to 2r divided by half is 4r, which implies x is 2√3r. Okay, so what you have now is 2√3r plus 2r. So b is 2√3 plus 2 times r. Okay, so now L over B is simply the ratio, 14 over this thing, so 7 over √3 plus 1. So this is this ratio. And we can also multiply and divide by the conjugate. So we can multiply like this to rationalize this expression. And we can multiply with the same thing on top. And so we get 7 times √3 minus 1 divided by 2, which is the form we're looking for. Yeah, 2 in the denominator is missed. Oh, no, we do get the 2 from this thing, right? Unless you, like, is it okay? Unless we're missing some other 2. This is square root of 147 minus 7. And then you have to answer like p plus q or something. So p plus q would be like 154 or whatever. Would be the answer at the end, whatever. But yeah, I'm being a bit negligent with the calculation here, but I think this is still correct. If you find some error, let me know. But the main idea was just to look at this triangle over here joining the centers, realizing the symmetry to get the 60 degrees first, and then getting this triangle. Either you can use law of sines, or you can use something called the law of cosines as well. So maybe I'll mention that briefly in case that'll be useful. Yeah. Oh yeah, 2 with the 2 and 14r. Yeah, the 2 cancel in the 14r, indeed. So you have this, you have B, you have C, you have A, and you have like this big A over here. So then you have the law of cosines, which is a square is equal to b square plus c square minus 2bc cosine of a. Yeah, which in the 120 case, if a is equal to 120, just means a square is equal to b square plus c square plus bc. So this is the law of cosines. This particular thing, it's called law of cosines. And it's quite useful as well. Like these two are the main trigonometric formulas you need at this stage, in case you're running to use trigonometry plus BC. Now this thing is equal to, okay, what is b square? So yeah, in this above case, it's 2r square plus 2r square. And the third thing is also 2r square, so into 3. So you can just use the law of cosines directly, you'll get 12r square. And this also gives you your x's. So therefore, x is equal to 2√3r. So you still get the same thing. Yeah, so you can do it one way or the other, whichever is more convenient to you. Generally, law of sines is a bit better than law of cosines, but sometimes you don't have enough angle information. Sometimes you may just only have one angle instead of all the angles. Like if the triangle was not isosceles, we would not have the other two angles being 30 degrees, in which case you need to use law of cosines. to get the calculation going. Okay. So any other questions about this problem, guys? Any questions about this one before we move on to the next? Yeah. I'll do the I'll do the next one, which is the twisted curve area thing, right? Yeah, that one's a bit easier, so it should be a bit faster. But before that, let's just confirm if everybody's okay so far. Any questions? I hope they clarified the denominator thing. Yeah, no worries, no worries. The 2 in the 14R, yeah. Mm, yeah. Any other questions, guys? Any other questions before we move on? All right, so moving onwards, we have question number 8, although I think I labeled 2 things as 8. So the earlier one is 8, then it should be 9, 10, 11. Unfortunately, I labeled both of them 8. Yeah. So we have this very hard to draw curve. So we have these 6 points shown the vertices of a hexagon, I think. And how exactly are we drawing the curve now? I'll just draw like a really badly drawn version of this curve. It's like a fidget spinner. Something like this. It's like a clover leaf fidget spinner type of curve. Yeah. So it has like these 3 arcs, right? So for every one of these. So you have vertices of this hexagon. Vertices of this hexagon. And you're just like spinning it around, right? Yeah, so you can split this at the 3 marks over here, which is where the hexagon meets. And again, the idea is quite simple. So you look at something like this. Then the hexagon joining the centers, let's say, each of length 2 pi over 3, where each of centers. What is the regular hexagon? What is the area enclosed by the curve? Oh, we already are given the perimeter. Sorry, I thought we had to find, yeah, we had to find the area. Yeah. Can you guys see my cursor? Yes and no, yes or no in chat, please, for the cursor. Mm, uh, can you guys see my cursor? Just a yes or no, please. It's only showing like 2 following, so I'm not too sure. Maybe the cursor dislodged. What's the area of the curve? Mm, yeah. So one idea I'll suggest is that if you're looking for the area of the curve, you can just look at the whole hexagon. Oh, sorry. Yeah, you can look at this hexagon over here. Okay, I don't have how good we are drawing it, but maybe you have the handout with you, right? So you can just see the diagram. It's quite hard to draw by hand. Yeah, the idea is that you can just look at the area of the hexagon minus the three outward sort of bulging arcs inwards, like the arcs which are bulging inwards, you subtract those. And yeah, so when you're looking at the area, okay, let me draw the hexagon first. Look at the hexagon, and then you have these inward arcs, right, which you're subtracting off. Like you're subtracting these three arcs off. All three of these are 1/3 of a circle, so combining is like losing one circle. So it's the area of the hexagon. Minus area of a full circle. Area of circle. Yeah, so you're subtracting these, and you're adding 2/3. You're adding 2/3 each time, right? So you're adding 2/3 of the area. So you're adding plus 3 times 2/3, which is plus 2 times the area of the circle. So the final answer for this problem would just be area of hexagon plus area of circle, right? And yeah, that's kind of the symmetry idea again. So we need to find the area of a regular hexagon of side 2, and we need to find area of a circle of radius 1. Latter we know is just like pi, so that is easy. This is pi. The vertex of a regular hexagon of side 2. Okay, this being pi maybe is a bit sus, a bit suspicious. We are losing a bunch of the area though, so yeah, maybe it's fine actually, because this was like there were 4 options, right? So I removed the options, so it's fine. It's not supposed to be an integer type thing, so it's fine. Yeah, we're removing like these. Yeah, so does everybody follow the idea? We're removing these 3 internal ones, which combine to give 1 circle, but we're adding these external ones, which combine to give 2 circles. So it's 2 circles minus 1 circle. It's total 1 circle that we are adding, and then we have the whole hexagon we are adding anyway. So it's hexagon plus circle, and the circle area is just 1. The hexagon area of side length 2 is what we have to find. Sorry, the circle area is just pi times 1. Yeah, the hexagon area is what we have to find. So you have a hexagon, which is regular, of side length 2. And you have to find the area of this hexagon. So firstly, let's do the angle sum thing. So the total sum of the angles is 4 times 180. So each angle is equal. So this is, so each angle is 120 degrees. So you have 120 degrees everywhere. So you have 120 degrees everywhere, which means 120 here and 30 here. So this is 90 basically. Yeah, this is pretty much 90 as well. So there's a more general way of computing area of a hexagon. Maybe that's a better thing. Maybe I should just do it using the circle method instead of this ad hoc thing. So if you draw a circle around this hexagon, which you can do because it's regular, each of these is 60 degrees, right? So this is 60 degrees equilateral triangle. So area of each slice is √3/4 times the side square. Side square. And side is equal to 2. Side is equal to 2 anyway. So area of each slice is √3, and you have 6 of them. So area of the whole hexagon is 6√3. So the final thing just becomes, I think, unless the calculation is off, but I think it should not be off. It should be, final thing is just 6√3 plus pi. Will be the final answer. I'll quickly confirm if this is correct, but let me know if you guys disagree, if there's any calculation issues, but this should be correct. Yeah, I think it should be correct. It's just a strange answer, that's all. But that won't be too surprising. This kind of thing happens. Mm. Yeah. Any questions? Let me know. We'll move on to the next one soon. Mm. Yeah. Any other questions in chat, guys? It's correct? Okay, okay. Yeah, this looks correct to me, but still want to make sure. Still want to make sure nothing is off. Going over the idea again. Mostly because it's a strange answer. It's like 6 root 3 plus pi is a very strange thing to get, but yeah, it's fine. It's not too bad. Yeah. Mm. Yeah, okay. Seems all right. Seems all right. All right, we can move on to the next question if no questions about this one. You also got that. Okay, okay. So yeah, no questions there. We can move to the next one then. Let me know if any questions about this one. We'll wait 1 more minute and then we move on to the next one. Okay, no worries. So we can just move on to the next one. It's not, yeah. Okay, sounds good. Yeah, it's a good thing to confirm the 6 root 3 plus pi is something people agree with. But at least the idea is clear, right? So we are removing these 3/1/3 of a circle because it's 120 over 360. And then we're adding these 2/3. So we're adding one circle to the whole hexagon. The area of the hexagon is √3/4 times radius square. And the radius was 2, so it's √3 times 6. Okay, so 6 root 3 plus pi. Yeah, so that's pretty good. No issues whatsoever. Okay, now we can move on to the next problem, which is, okay, so now we have the 3 hardest problems in this set. We can only do like, okay, it'll take a while to do each of these perfectly. So I'll give you a hint for the 8th one, although it should be 9th. And maybe we can do the 10th one. So I'll give you a suggestion for what to do for the 8th one. Okay, so for the 8th one, so it'll take too long to do the full calculation for 8th, but I'll give you a suggestion. You can try something like, so because you have square root of 2x minus xy, right? Plus square root of 2y minus xy. So yeah, this is equal to 1, for example. Like, let's say you're trying to solve this type of equation. Okay. Now, firstly, you know that x, y, z are positive. So you're given that they're positive numbers. And so 2 minus y also should be positive, and 2 minus x should be positive. So x, y, and z are all less than 2. So one substitution you can do is x equals 2 times something, which stays below 1. And you want to get rid of the square root. So you want to make it a square, and you want it to be something trigonometric if you want to force geometry here. So there's a trigonometric substitution, which is x equals 2 cosine square a. If you want to do that, yeah, you can do this. And you can do y equals 2 cosine square b. If you make this substitution, you'll get something interesting. So now square root of 2y minus xy is y times 2 minus x. So y is now 2 cosine square b. if you make the substitution, and x is now 2 sine square a. So when you take the square roots, you'll get 2 times cos b sine a, something like that. And then similarly, you'll get sine b cos a. So when you add them, you'll get sine of a plus b. When you add them, you'll get sine of a plus b is equal to 1/2. Similarly, you'll get sine of b plus c and sine of c plus a. You can find what these values are. B plus c is 1/√2. And then finally, you'll get sine of c plus a is equal to √3/2. You can even replace these by angles. So you can say like 30 degrees, 45 degrees, 60 degrees internally, and then try to solve for ABC. So you can do that, and then you can solve for ABC. So I won't do the full calculation here, but you can try corresponding this to like 30, 45, and even like, yeah, 60. You have to be a little careful if you're trying to do it as a proof, because then you also want to make sure it's correct in a period, like it's not like 135, for example. So you want to make sure all of these are correct, and you can like solve for ABC using this. And then the 1 minus x, 1 minus y, 1 minus z thing will just sort itself out. So it'll be like 1 minus 2 times cosine square a. Cosine square a is simply minus cos 2a, right? So it's a double angle formula. And once you know the value of angle a, you know what cosine of 2a is. So you can just do that. You can multiply these, square everything, and compute the answer. So I'll just leave the computation to you as an exercise, but this is roughly the idea. And this is quite powerful. In general, if you have variables which are between 0 and 1, and you know the positives, substituting like sine of x or sine square of x or something is usually a good idea. Like this kind of trigonometric substitution, especially when you expect you'll get some sum of angles property. So this is sine a cos b plus cos a sine b. If you expect something like this will happen, then it's always a good idea to do this. Because now you can solve for the angles individually. Yeah. So this will be the strategy, but I'll not do any calculation here because I think it'll actually take a while to do the calculation. And it has some risks of spending our remaining 10 minutes doing calculations, so not too great. Yeah. For the 9th one, I'll also give a small hint, and then we can ignore that. Although it should be 10th, not 9th. Numbering is bad. And this is only for students who've seen complex numbers. So if you've not seen complex numbers, you can try something different. But if you've seen complex numbers, then you can look at this relation. E to the I theta is cos theta plus I sine theta. You can look at this relation. Yeah. And so, okay, with this relation, you can similarly substitute minus theta, which is minus I theta equals this thing, cos theta minus I sine theta. And now you can solve for sine of theta. So you have a system of linear equations in 2 variables. So 2i sine theta is the difference. And so sine theta is 1/2i times the difference, e to the I theta minus e to the minus theta minus I theta. So if you want, so I'm just mentioning this as a technique. I mean, you can use this technique, you can use something else. So sine theta. So it's the general formula for sine theta using this. And so if this is z, where z is a root of unity, then you have like 1/2i. So I hope everybody understands this, or at least this. If you've not seen it, you can ignore it. So okay, if you've not seen complex numbers before, you can completely ignore this approach. If this looks magical, then you can ignore this for now and worry about it later. If you've seen it, then this could be useful. And that's the only reason I put this problem is because it could be useful if you've seen it before. Sorry, z minus 1/z, where z, you can even have z to be a root of unity. So if like z to the n is equal to 1, when z is of the form e to the 2 pi I divided by n. Right? Or you can even have e to the pi I is -1, which is the famous Euler equation. And you can use this as well. So you can use all of these and work with the roots of unity, and then you'll have interesting things like 1 plus z square all the way, plus z to the n minus 1. This whole thing will be equal to 0. You can have things like this as well. So all these complex number relations will help you understand the trigonometry sine of theta, because, for example, sine of 5 degrees is equal to 1 over 2 pi, 1 over 2i, sorry, or 2i, z minus 1 over z, where z is equal to e to the 2 pi I divided by like 20. I'm not 20, sorry. 36, 60 by 72, sorry. Or e to the pi I by 36. Yeah, this is probably better for our purposes. So you have z to the 36 is -1. -1. Or you have -1 over z is like z to the 35. And so you can use this, you can use a bunch of other relations, and you can come up with some sums. So you can use it to simplify the sine summation thingy. That's one approach. Or you can try to fuse like sine 5 with like sine 85 or something, or you can try fusing sine 5 with sine 175 or something. It's up to you. The choice is yours. I mean, there's so many things to do. And pretty much all of them will have. Yeah. Yeah, you can fuse sine 5 with sine 175, or to get like 2 times sine of 5. And then you can do like sine of 5 with sine of 85. Use like some kind of formula there. So the sum of angles formula for sine 5 plus sine 85 is also something you can try using. Yeah, there is plenty of things you can try using. And then at the end, you can use this type of complex number series if you want. So this is the idea for problem 9, but it'll be complicated. So that's why I said like 8, 9, and 10 will be a bit complicated, because they assume some trigonometry and some complex number theory, which we don't have time to go over in this meeting, but maybe in the next meeting or sometime we can go over this complex number stuff. We can go over maybe problem 10 in like full detail. Like maybe we can do problem 10 completely. So let's see if we have time for problem 10. Okay, so I'm on the complete right side of the page now. The problem 10, this is the last problem we have. So let's see. Yeah, you have XYZ satisfies some equations. X equals square root of y squared minus 1 over 16 plus square root of z squared minus 1 over 16. Yeah, we have both of these equations. So either you can try solving this whole thing algebraically, or you can think of some geometry here, because it looks like you have some kind of reverse Pythagoras thing, right? You have a square root of a difference of squares. So there's some reverse Pythagoras thing seemingly happening here, right? So x squared minus 1 over 25 plus z squared minus 1 over 25. And you have z is equal to square root of x squared minus 1 over 36 plus y squared minus 1 over 36. So you have these equations which are a bit awful. Like if you try to solve this algebraically, it'll actually be pretty impossible, to be honest, because if you try to square everything, you'll have a 2 times square root of y squared minus 1 over 16 times z squared minus 1 over 16. You have to square everything again, and then you have like a huge degree polynomial on the first equation itself. Similarly, in the second and third, and it'll just be impossible to solve algebraically or by hand, right? So you need some level of cleverness, and you're trying to find x plus y plus z, for example. So you need some level of cleverness here to find this thing at the end. So one strategy is that you can think of this as a triangle. You can think of triangle XYZ. You can think of triangle XYZ, where the opposite sides are x, y, and z. So these are x, y, and z. Okay. And now, how do you get square root of y squared minus something? So you draw a perpendicular, let's say, and let's say this perpendicular length is hx. Then you actually do have a normal relation, right? Yeah, let's say this is a. Then yz is equal to ya plus za. Yz is equal to ya plus za. And so this is equal to square root of y squared minus hx squared plus square root of z squared minus hx squared. This whole thing is equal to x, right? And we are given that this is true if hx is 1 over hx squared is 1 over 16, which means that hx is 1 over 4. Like, this is the only thing which will satisfy this equation. Otherwise, you'll have something too low or too high. So h is equal to 1 over 4. So hx. And similarly, hy is 1 over 5. Hz is 1 over 6. 1 over 6. So you actually do get this calculation. You know the altitudes of this triangle now. And now you can notice that x times hx is equal to y times hy is equal to z times hz is equal to 2 times the area. 2 times area of triangle XYZ. Right? So it's like 4x is equal to, so x is equal to, so x to y to z, we know the ratio now. It's like x is equal to 4 times some constant t. Y is equal to 5 times some constant t. And z is equal to 6 times some constant t. Right? And now we just need to find what this constant t is, and we'll know all of the sides of the triangle. So let's just use the first equation. We have 4t is equal to square root of, so it's y squared minus 1 over 16, right? So it's 25t squared minus 1 over 16. Plus square root of 36t squared minus 1 over 16. And this is manageable. This is something you can solve. It's just an equation in one variable. So you can square it up and try to solve it. Solve this for t. And this will give you all of the x, y, z. And the final answer, x plus y plus z, is like 4 plus 5 plus 6 is like 15t. So we are looking to find 15t, and that'll be it. This is what we want to find. So this will be approach for the last question as well. So I told you the sort of overview or hint for these 3 problems, but I think it'll still take a lot of work to complete these solutions.